Hi, in this lecture we will discuss the one definition called pairwise relatively prime integers and its related results. First, the definition of pairwise relatively prime integers. The positive integers a1, a2, etc. an are pairwise relatively prime. Pairwise relatively prime if every pair of integers is relatively prime. If every pair of integers is relatively prime. That means a set of integers a1, a2, etc. an are said to be pairwise relatively prime if we consider any pair a1, a2 or a2, a3 or any pair of integers, then they are relatively prime. Then we can say that the set is pairwise relatively prime. That is, we can write GCD of AI comma AJ equal to 1 whenever I not equal to J. So whenever I not equal to J, GCD of AI AJ equal to 1. This is called pairwise relatively prime definition. Now, for example, consider the numbers integers 8, 15 and 49. So these are if we consider any pair, that means a GCD of 8 comma 15 equal to 1 and 15 comma 49, this that is also equal to 1, and 8 comma 49 there they have also no common factor other than 1. So all these are pairwise, all these are relatively prime. That means this set is relatively pairwise relatively prime. But when we consider the integers 6, 25, 6, 25, 77 and 91, these are in this case, okay, in this case 6, 25, 77 and 91, they are not pairwise relatively prime, since in the reason we know that 77 is 11 into 7 and 91 is, we can write it as 13 into 7. So when we consider the pair 77 and 91, their GCD is equal to 7 and not equal to 1. That means this pair is not relatively prime. So we can't say that the set is, we can say that this is not pairwise relatively prime. Now, there is a corollary related to this concept, corollary of the same theorem that we discussed in the last preceding lectures. Now, corollary 3.7, it states that if the positive integers a1, a2, etc. an are pairwise relatively prime, if the positive integers a1, a2, etc. an are pairwise relatively prime, or pairwise relatively prime, then GCD of A1, A2, etc. An is equal to 1. Okay, so the corollary is if the positive integers A1, A2, etc. An are pairwise relatively prime, then their GCD will be equal to 1. So this is an obvious result. Um, For instance, they consider the integers, if we consider the integers 8, 15, 49, these numbers are relatively prime, are pairwise relatively prime. A GCD of 8, 15 is there is no common factor, it is 1 other than 1, and 15, 49, there is also no other common factor 1 than 1. Then 8 comma 49, they also have no common factor other than 1. So these are pairwise relatively prime. Then by the corollary, then GCD of 8, 15, 49 is equal to 1. Okay, but the converse is not true. Remark: the converse of the corollary 3.7 is not true. That is what we need to prove, that if uh, GCD of A1, A2, etc. An equal to 1 need not imply that A1, A2, etc. An are pairwise relatively prime. For example, consider the numbers 6, 15 and 49. We know GCD of 6, 15 and 49. They have no common factor other than um, 1. So their GCD is equal to 1. But we can see that GCD of 6, 15 equal to 3. Therefore, the three numbers are not pairwise relatively prime. So if the GCD is 1, GCD of A1, A2, etc. An equal to 1 need not imply that they are pairwise relatively prime. This is such an example. Okay. Now we come to the last corollary. Corollary 3.8. The result we have already proved in two different ways. Now the result is there are infinitely many primes. This we have already proved in two different ways, and this is another method from the theorem. So proof is again by contradictions. Suppose there is only, without loss of generality, assume that there is only a finite number of primes. Let it be P1, P2, etc. Pk. Now consider the Fibonacci numbers. FP1, FP2, etc. FPK. Since they are pairwise relatively prime, uh, we have already proved that all the Fibonacci numbers are relatively prime. So clearly, all the Fibonacci, all of them are pairwise relatively prime. So there are only k primes. Since there are only k primes, each of these Fibonacci numbers has exactly one prime factor, isn't it? We know that we have already proved that Fibonacci numbers are any two Fibonacci numbers are relatively prime. That means they are f1, fp1, fp2, etc. fpk are pairwise relatively prime. Okay, and since there are only k primes, each of these Fibonacci numbers has exactly one prime factor, has exactly one prime factor. Okay, that is each is a prime. Exactly one prime factor, that means each Fibonacci number is a prime. Each is a prime. But this is not true. This is a contradiction. But this is a contradiction since we consider f19. We know that 19 is a prime number and we have f19 is actually 4181 and this can be written as 37 into 113. So this is a composite number. If 19 is a product of two uh, numbers, 37 into 13 is a composite number. So all the Fibonacci numbers are prime is a contradiction. This is obtained because we have assumed that there are only finite number of primes. Hence, there are infinitely many primes. Hence, there are infinitely many primes. Okay. So our section 3.1 is over. We can stop here and you can do the exercise portions. Exercise, try the questions in the exercise 3.1. If you have any doubts that we can clear in the next class. Okay, thank you.